Swayam Prabha. Digital India. Educated India.
So, we can also talk a little bit further about what these Lagrange multipliers are actually saying. And for that, let us go back to our example again, and I will tell you what. So, you can actually calculate what the lambda star in this particular case was, and what you will notice is that in this case, actually, if you take, write it in a different color. So, if you take the lambda star actually satisfies this. It's if I look at this optimal value m of alpha and look at the partial derivative of m of alpha with respect to alpha, then that is actually lambda star. So, that is, in short, it is equal to 2ab. Now, what is the meaning of this? What this means is that the lambda star is telling me how much would the objective function change if I changed my alpha. How much would the, not the objective function, the optimal value change if I change my alpha. So, m of alpha, remember, was the size, was the area of the largest rectangle. It is a function of alpha. Alpha was the right hand side here. So, alpha tells you how big is your ellipse, right. If I scale alpha, my ellipse magnifies or becomes smaller. So, if I change my alpha slightly, how much would the size of the largest rectangle, how much would the area of the largest rectangle change by? That is what my lambda star is telling you. A lambda star is actually equal, is the derivative of the optimal value with respect to alpha. So, here is the interpretation and the importance of Lagrange multipliers. Lagrange multipliers are telling us how sensitive is the optimal value to changes in the constraint. So, think of the constraint as a resource. Okay, suppose I tell you that alpha is the size of my controls, say, the size of the plot of land, which is of this elliptical shape plot of land, and alpha controls the size of that. So, alpha is a way by which I am going to measure the size of that plot of land. If I wanted to change my alpha a little bit, means if I wanted to go for a slightly bigger plot of land, how much bigger of a rectangle could I accommodate in that in terms of area? Well, the answer is, for a delta alpha change in alpha, it would be lambda star times delta alpha would be the change in the area of the optimal of the largest rectangle. Okay. So, Lagrange multipliers tell us something about the so this is what is called sensitivity. Sensitivity is for small change in constraints what is the change in optimal value. So, small changes in the constants of the constraint, what is the change in the optimal value. So, you can do this one constraint at a time also. You do not need to look at all constraints together. Look at, if you are changing only one constraint by a slight amount, you look at how much is you are basically just making a change in that particular component of alpha. Okay. So, what together by together with these you will be able to say what the, so I'll explain what this is. So, you can get in the general case, if I look at just so this is the derivative of the optimal value with respect to alpha, that's always equal to lambda star transpose. Now, one thing to note here is because you are talking of equality constraints, because you are on surfaces, right, a bigger value of alpha does not necessarily mean you have more resource. It just happened because we are talking of this ellipse, that larger alpha would mean a bigger ellipse and smaller alpha would mean a smaller ellipse. But in general, as you change your alpha, your surface can change in many in strange ways. So, it does not necessarily mean that you are optimizing over a bigger region, or that the earlier region is enclosed in the previous region, or any of that. Okay, because we are talking of surfaces here. As alpha changes, the shape of the surface or the contour on which you are operating will change. Okay. So, it is possible that the objective can, by increasing alpha, your objective could decrease, or it is possible that by decreasing alpha, your objective could increase. All of that is encapsulated in the sign of lambda. Lambda is also then, the sign of lambda also tells you which constraints are sort of more binding than the others, and in which direction should you be changing the constraint, whether you should be decreasing or increasing in order to get a better objective. All right. Okay. So, we were doing this problem of last time we did this problem of least squares solutions of equations that were overdetermined, right. So, these were, so you could not satisfy all equations at once. We did this in the context of machine learning and also in the context of maximum likelihood estimation. So, so all equations could not be satisfied together by a linear function, by a linear relation. So, we were looking for the minimizing the sum of the squares of the residues. That was the problem we were looking at. That became an unconstrained optimization problem. So, today I will look at a slightly different problem. So, here suppose you have a matrix A, and since this matrix is a fat matrix. What I mean by this is, you should imagine it to be something like this. It has fewer rows and more columns. This is the nature of the matrix A. Okay. So, it's and let us assume that it is full row rank. Now, if I ask you for a solution of this Ax equal to b, okay, where b is some other vector. So, suppose my A is in Rm cross n and b is in Rm, sorry, and I ask you for a solution of Ax equal to b. And so, I am in this region where m is less than n, actually m is much less than n in general. Okay. So, then can you solve for x, and how many solutions do we have? Yes. So, there are fewer, so number of unknowns here is n, which is the number of columns of A, and number of equations is m, which is the number of rows of A. You have fewer rows than columns, or fewer equations than variables. So, you can easily of course solve for this, and in fact, you will get not one but infinitely many solutions. Why infinitely many? Because you can, this sort of matrix, a fat matrix like this, will always have a null space, right. So, the null space of A of A, this is Z such that Az equals 0. So, this is an entire subspace of Rn, right. So, if I have one solution like this x hat, suppose if I take x hat, let x hat be such that Ax hat equals b, and I take any z in the null space of A, then what can I say? X hat plus z is also a solution of this, right. So, if I have one solution, and of course, there is at least one, I can always generate an infinitely many more by just picking points from the subspace, all right. So, then in this sort of situation, then a common problem that is posed is that you want to find a solution that has a certain structure. Now, structure can mean many different things. Okay, structure can mean sparsity, structure can mean close to something else, structure can mean having the least norm. Okay. So, in this case, let us look at the least norm problem. So, the problem there is to look at amongst all solutions x of the system of equations A x equal to b, you want to find the one which has the least norm. So, x transpose x, or x transpose x, that is the same as norm of x whole square. So, we have this problem. Okay. So, now if A is in R m cross n, how many variables are we optimizing over? You have n variables here, x is in R n, right, n variables, n scalar variables. How many constraints do we have? M of these, right, all of them are put together. I have written it as a matrix equation, but it is basically m individual scalar constraints, right, n variables, m constraints. So, this is now an optimization problem of trying to find the solution of least norm that satisfies a linear system of equations. Right. Let us solve this. So, remember this this function L that I introduced. If you look at this function L, okay, and I write here, just look at this quantity, the gradient with respect to x of L. What would that be? That would be f0 of x minus gradient of f1 of x times lambda 1 minus gradient of f2 of x times lambda 2 dot gradient of fm of x and lambda m, correct. And now go back to the boxed equation here. Can you write this equation in terms of this function L? This is, I mean, if I just take the transpose of this, what this is effectively would amount to is to simply say it would amount to saying that the gradient of this Lagrangian equation with respect to x evaluated at x star lambda star should be equal to 0, right. So, this box equation is all it is saying is that the gradient of the Lagrangian must be equal to 0. So, this is one succinct way of writing this equation, the red box equation. In addition, of course, you need to satisfy your these boxed equations. Okay. So, let's use that sort of notation here. Okay. So, let us write the Lagrangian. So, what would be the Lagrangian? I have my objective x transpose x and minus, now I need to write, so what I can go back here if you like. Lagrangian was linear you are taking linear combination of the constraints, right. So, the constraints were okay, so yeah, so these constraints were written as f yeah, so actually I made a slight error here. Let me just correct that. So So let me absorb all the alphas also in the definition of the function. So if f1 of x minus alpha equal to 0 is my constraint. Okay. So if so it's lambda 1 times f1 of x minus alpha lambda m dot 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 lambda m into fm of x minus alpha. This does not affect the way after I take the partial derivative with respect to x, all the alphas will not will anyway go away. So it doesn't affect this condition. Okay. So let's write it in this sort of way. So I can write it as for my problem. So you have x transpose x minus, now let lambda be your Lagrange multiplier vector, and I will do lambda transpose Ax minus b. Now, can you verify that this is the same as doing actually lambda 1 into so where A can be expressed as A1 transpose dot 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 AM transpose. So if my rows of A are A1 transpose, A2 transpose and AM transpose, those are my rows of A, okay, then I can write this Lagrangian in this sort of way. Right. So, it is x transpose x minus lambda transpose A x minus b, where now lambda is a vector is just any vector in Rn. So, what I have to solve for is my previous boxed equation, which is the gradient of the Lagrangian should be equal to 0, and in addition to that I need to make sure I am feasible, which is this other boxed equation, okay, which means I need to make sure that Ax equals b. These are the equations I need to solve. Is this clear? So if I put the gradient of the Lagrangian with respect to x, let's calculate that. What would that be? What is the gradient of the Lagrangian with respect to x? So it's 2x minus A transpose lambda. So it's 2x minus A transpose lambda. So this is my this is the Lagrangian. I am taking its gradient with respect to x. It gives me 2x minus you can check this. This is 2x minus A transpose lambda. So I need to put this equal to 0. So that gives me that x is equal to A transpose lambda divided by 2. Okay. Now I also need to satisfy Ax equals b. So I can just substitute for this x out here, and that would give me A into A transpose lambda by 2 equals b. Now A into A transpose, remember A was a fat matrix like this. A transpose would be a thin matrix. A I have assumed is full row rank. So A into A transpose is invertible, right. So consequently, I can take this on the other side, and So, I have A transpose whole thing inverse B and a 2 outside. That is my lambda. With my lambda known, I can put it back here to get back my x. So, this is my lambda star, lambda equals lambda star as this, put this back here and that gives me my x star as equal to A transpose A transpose inverse B, sorry, into, yeah, there is no 2. So, this is your least norm solution. Okay. So, the least norm solution of this optimization problem is this one here. So, everyone understood the what we did. We had our optimization problem. We wrote out the Lagrangian function. Then we took the gradient of the Lagrangian with respect to just the x variable, put that equal to 0, and then we had to also satisfy our constraints. These were the two equations we need to satisfy. You put that in, we get that we found actually that there is a unique solution. So, it has to be therefore that this is the solution of your problem. Is this clear? Okay. Okay. All right. So, so I will, so we can end here. We will continue again next time.